Hello, I'm Dave. Welcome to my Technical Notes channel. If you've got a battery powered project, you need to have a good idea of what your battery capacity is. So conventional methods are not particularly accurate. So I'll show you how to improve the estimation of remaining battery capacity. So conventionally then we would measure battery voltage, measure 4.2 volts and say the capacity is 100%, or measure 3.85 volts and say the capacity is 50%, and when it gets down to 3.5 volts we'll assume the battery is empty. That sort of works, but actually it's not very accurate. So LiPos have a fairly well defined voltage against charge used curve, and there I've drawn it out for you. When you've used no charge, the voltage is 4.2 volts, and 100% charge approximately 3.5 volts. So we can use that to our advantage in improving the estimation. Now let's compare the two different curves, or the straight line approach, what I'm calling conventional approach. When the voltage is 4 volts conventionally, 72%, but actually the capacity is more like 88%. Similarly, when you measure 3.85 volts, the capacity is more like 72%, and so on. And down at the other end, when you measure 3.6 volts, the capacity is actually 10%. It's less than you think. So it's important to get this right. So the best way of doing this is to find an equation that matches the LiPo discharge curve, and I've actually done that for you. So the task is to find an equation that matches the curve. It's using a polynomial solving process. Most polynomials start off life as a straight line graph, or y equals mx plus c. And I solve mine using a tabular approach, but you can find out how to do that using Google, how to create a polynomial. So I've shown there the equation for the underlying straight line, which is dy by dx, so delta y over delta x is the gradient, and then when x equals 3.5 there's an intercept of 500. It works out. So having got our equation, we now need to convert it into C++, something we can use in our sketches, and there again I've done that task for you. So first of all, read the voltage from the analog to digital converter. I'm using an Arduino Uno input, or a Wemos D1 mini input A0. Using ESP32 it would be pin 36 or 39 or 35 depending on the board type. Convert that into percentage using the polynomial, and then just do some tests to make sure that if the voltage is much more than expected, hold the percentage to 100%, or if it's much less than expected, put it to 0. So at the end of this calculation we have a good estimate of the remaining percentage of charge. So here's the final code for the ESP32. This one's for the Lowlin D32 board, which has an onboard voltage divider, and therefore it uses the ADC pin 35. The 7.23 value is a calibration figure, so ideally measure the input voltage to the ADC and then adjust the reading you get for voltage on the serial port by varying that 7.23 value. So here's the same code for the Node MCU. Actually there's no difference, but to note that you have to put, because that board doesn't have a voltage divider, you need to add one, and two 100k resistors which divides the voltage into two is the way to solve this, and in fact it's what's used on the Lowlin D32 board, so the code remains identical. The only thing you need to change is the analog read statement is on pin 39 or 36. whichever one you choose, otherwise known as VP and VN. On the ESP3266 Wemos D1 Mini, that does have a voltage divider on board, and it just needs to be augmented with a serial 100k resistor, effectively improving the voltage division. Its normal input range is 0 to 3 volts, so adding that 100k puts it well over to 0 to 5 volts. So that constant value has now changed down to 4.24 to reflect the different value of input divider. For the Arduino Uno, its normal input range of an ADC is 0 to 5 volts, so it makes it easy to scale the values, but again, no difference in the function or equations other than getting that analog input voltage on A0 or A1 or 2 or 3 or 4 or 5. Change the voltage analog read line accordingly. Here's a summary of all the connections required for the different boards to measure battery voltage. I think that's fairly self-explanatory. So the Lowland D32 has an onboard voltage divider, direct connection to the battery. Similarly for the Uno, direct connection for the battery, whereas the Node MCU 32 board needs a voltage divider adding, as does the Wemos D1 Mini, or its onboard voltage divider needs to be augmented with a series 100k resistor. So in summary then, implementing an improved battery estimation using some mathematics called a polynomial equation, which is the best fit to the LiPo battery discharge voltage against capacity curve, gives you an overall improvement in battery capacity estimations. Even uncalibrated, it gives you much better results than the conventional way of measuring battery capacity. Just simply measuring voltage and converting that to percentage isn't terribly accurate. And if you can calibrate your battery voltage using a DVM and adjusting those calibration values that I indicated in the code, you can get really good results, and it's easy to implement. It's software based, and it's a self-contained function that reads the voltage, calculates the estimated capacity, and returns the value. Well, I hope you found that useful. I hope you found this technical note interesting and useful.